Okay, so we're trying to prove this theorem of Kleitman and Winston, and we're going to do it using the method of Ferber, McKinley, and Samorty. And they proved this this container theorem for C4 free graphs, and so this was a slight weakening of a theorem of myself and David Saxton. But the point is that the proof is much simpler and allows a generalization to an arbitrary bipartite graph. Okay, so that the purpose of what I'm going to tell you is this is an argument that works for C4 free graphs, but also works with only slight complications for basically an arbitrary bipartite graph. Okay, it's easier to illustrate it in the case of C4, just because it makes the calculation, the statements a little bit simpler, easier to digest. Okay, but you can basically go home and try to do the same thing for an arbitrary bipartite graph, and there's a decent chance you'll be able to figure out the details. Okay, so we're going to try and prove this container theorem, which implies the Klein-Winston theorem just by taking k to be a large constant. What do you do? What does it say? It says that each container, so we have a set of containers, so B tells us that they're containers for the C4 free graphs. Each one has at most k times n to the 3/2 edges, where we can choose k anything larger than a large constant. And for each k, we get a corresponding size of the family of containers. Okay, so as k gets bigger, the family of containers gets smaller. Okay. Right. And so to prove it, we're going to apply the container lemma to the 4 uniform hypergraph encoding C4s. But as we apply the lemma, we're going our vertex set, which starts out being the edges of the complete graph, is going to get smaller and smaller and smaller. And so after some long period of time, we're going to have a graph. So our current container will be a graph with something like k times n to the 3/2 edges. Well, that's what will be at the end, and we need to make sure the set of containers isn't too large for that hypergraph. We need to define a set of C4s in our graph, which we can apply the container lemma to. Okay, so that's going to be our challenge. So just to recall, so this 4 uniform hypergraph, when our current container that we're applying the lemma to in this iteration has k times n to the 3/2 edges, then in order to have the correct number of containers, we need to have tau to be about k to the -4/3. Right? And this 4/3 isn't really important. It's important that it's bigger than 1 for the application. Okay. And 4/3 is just something that comes out nicely in the from the supersaturation theorem. Okay, so in order to prove this, it turns out that it's sufficient to prove the following called balanced supersaturation theorem. So the main thing that I want to tell you about today is this concept of a balanced supersaturation theorem and why it's useful in the container method. So far, all of the supersaturation theorems that we've seen have just been of the form, if you have enough edges or whatever, then you have lots of copies of your forbidden subgraph. Or if you have enough vertices of your hypergraph, then you have lots of edges of your hypergraph. And right, then that's often enough. But in this situation where we're applying the container lemma not just a bounded number of times, but log n times, we're going down from the complete graph down to something much sparser, then the simple supersaturation is no longer enough. So we can't just fix things by taking the constant larger. So the constant in the container lemma. So what we need is something. Here's a simple example of the kind of thing we need. So we're given this graph with k n to the 3/2 edges. We need to find a bunch of copies of C4 in G. We need to find many of them, like in supersaturation, but we also want them to be sort of well balanced. So just like in the container lemma, we need the edges of the hypergraph to be well balanced. We need them to satisfy these maximum degree conditions. So this is just an attempt to sort of force these max degree conditions. So each edge is used in at most k to the 4 members of A is just saying the maximum degree of our hypergraph is going to be at most k to the 4. And this B, each pair of edges is used in at most k squared members of A. That's just saying that delta 2 of our hypergraph will be at most k squared. Okay, so let's just see, once we have this, what tau it gives. So first, so our number of edges of our hypergraph is k to the 5 n to the 3 over 2. Our number of vertices is k n to the 3 over 2. So our average degree is roughly k to the 4. Okay, so the average degree of this hypergraph A, so A is a collection of C4s. It corresponds to a 4 uniform hypergraph with vertex set, the edge set of G. This hypergraph has average degree k to the 4. Okay. Now, because each edge is used in the most k to the 4 members of A, that means that delta 1 of A is at most k to the 4, right? Because an edge of G is a vertex of the hypergraph, and a C4 is an edge of the hypergraph. Okay, so this is just exactly condition A. And that's what we wanted, because remember, delta 1 of A has to be at most a constant times the average degree. So the max degree is at most k4, and that's at most a constant times the average degree, which is also of order k to the 4. Okay, this twiddle, it corresponds to this omega as a constant factor, hidden constant factor. Okay, so that deals with delta 1. Delta 2 by B is at most k squared. Now we need in the container lemma that to be at most tau times the average degree up to a constant factor, which means that tau has to be at least 1 over k squared. Okay, so any tau at least 1 over k squared satisfies this delta 2 condition. We also have to satisfy the delta 3 condition, but delta 3 is trivially at most 1 because only 3 edges are in at most 1 C4. That should be at most tau squared times k to the 4, which again gives tau at least k squared. And finally, we need a bound on delta 4, which again is 1. Every 4 edges are at least in at most 1 C4. That needs to be at most tau cubed times k to the 4 to apply the container lemma. And that's true as long as tau is at least k to the minus 4/3. So this is the most difficult condition to satisfy. So that's the one that we can take. So that if we take tau equal to 1 over k to the 4/3, the hypergraph A satisfies the conditions of the container lemma. Okay, so if you've forgotten the conditions of the container lemma, then this is what they were. Okay, so you need that delta 1 is at most constant times the average degree, delta 2 is at most tau times the average degree, delta 3 is at most tau squared times the average degree, and delta 4 is at most tau cubed times the average degree. Okay, those were the 4 conditions in the container lemma. Okay. So this means if we can prove this balanced supersaturation theorem, then we can apply the container lemma with the tau that we wanted, and then just running through the usual argument, we get this container theorem. Okay. So I'm skipping the details, of course. I think it's a good exercise to go and check them. And if you get stuck, then you could look at the paper by Ferber, McKinley, and Samorty, or my paper with David. But anyway, so this reduces the problem to proving this balanced supersaturation theorem. Are there any questions about that?
Yes, Rob. What happened with the remaining C4s in G?
When you what? Sorry.
What happens with the remaining C4s?
Thank you. Yeah, so they're just extra conditions, but that just helps you. So that's information you're allowed to ignore. So you have to, it's slightly confusing which way the monotonicity goes, but right, it's all right. So you're an independent set in all the C4s, so therefore you're an independent set in these C4s. And therefore your containers that you get will also be containers for the independent sets in the original thing.
Right.
Right, so yeah, so it's the monotonicity goes the right way. Yeah. So we can happily just ignore them, which is fortunate.
Sorry, Rob. So yesterday you said that these numbers are kind of best possible in some sense, right? So
Sorry. So yeah. So these are not best possible. Best possible is k squared.
Sorry,
So
where in k squared in the A or?
Sorry. So this balanced supersaturation theorem is not best possible. The best possible one is slightly more technical.
But
yeah. So it's right for C4s. It's not much more difficult to prove, but the proof doesn't generalize.
Yeah.
So I'm proving a weaker one with a proof that generalizes.
But best possible in the sense that, like, if you take something like a random graph and it satisfies these numbers, or in which sense?
This one is not. This one is not.
No, but I mean, like the best.
Our best possible. Yeah. So ours is best possible. So the construction is, it depends on the value of k, but the interesting construction is when you take a projective plane or something extremal for C4, blow up the vertices, and replace edges with matchings.
Mm-hmm. Yeah. Okay.
Yeah, random matchings, I guess. Yeah. Right. So there are. I'll mention the. Yeah. Sorry. I'll mention our container theorem, but not our balanced supersaturation theorem. But it's similar, just the numbers are a bit different, and it's a bit harder to prove. So notice that in particular. So here, this is not the optimal number of C4s, right? If you have this many edges, you can actually get k to the 4 C4s. I'll get this right. What do I mean? K4s n squared, k to the 4 n squared, I guess. K to the 4 n squared C4s. So they ask for fewer C4s, but it's enough for the application. So it's not always best to look for the largest possible number of C4s, surprisingly. I mean, best if you want the sharpest result, not best if you want the simplest proof. Anyway, so the proof is very nice and simple. Sorry, so are there more questions? Okay. So the proof of this is very nice and simple, and also it sort of illustrates some general ideas which seem to be useful for these kind of things. So how will you prove such a thing? So one sort of very important idea seems to be not to find all of the C4s at once, that we should find them one at a time. And this is doing so makes it much easier to control these maximum degrees. Okay, so instead of finding all the C4s at once, we're gonna have this collection A, and we're gonna add one C4 to it in each step. And how are we gonna do that? So we're gonna find lots of C4s. So we're gonna have a collection A that we've already found. And if it were this big, would be done. It's going to always going to satisfy A and B. And if it were big enough, then we're finished. So suppose it's not big enough. Then we're going to try and add one C4 to it. So we're going to find this many copies of C4, none of which mess up condition A or condition B. So none of which contain a, sorry, I've written vertex here. I mean vertex of the hypergraph, but I mean edge of the graph. Sorry. So this should really say none of which contains an edge of G that's already in k to the 4 members of A, or a pair of edges of G that are already in k squared members of A. Okay? So you're going to find a bunch of these good copies of C4 that don't mess up condition A or condition B. And because we found this many of them, at least one of them will be new. And that new one we can add to the collection. Right? We can only add one because we only know that each one individually doesn't mess up our conditions. Okay? So there are going to be certain edges that are saturated, meaning that they've already reached their limit, k to the 4, and a bunch of pairs of edges that are saturated, meaning they're already in k squared members of A. And we are not interested in copies of C4 that contain one of these saturated edges or saturated pairs of edges. We want to find lots of copies that are not saturated, that contain no saturated edge or pair of edges. Okay? Right, so if A is not yet large, then at least one of these is new, and so may be added. Okay, is that vague strategy? Does it make sense? Okay, very good. Right, so how do we do this? Okay, so so this idea is from my paper with David Saxton. Here's the idea from Faber, McKinley, and Samorty. Right, so we're going to choose a random subset of a certain size, about size n over k squared. So this should look familiar from the supersaturation theorems that you were proving in the exercises. Okay. Now, I'm going to remove all edges of the graph that are already in k to the 4. Yeah, sorry. Hello? Question? No, perhaps not. So please ask questions at any moment. So we're going to remove all the edges that are already saturated, and we're going to remove one edge from each pair of edges that are already saturated. Okay, so these things are we don't want to use these edges, so let's try to avoid them. And the point is, because of the choice of P, we're not going to remove too much. So the problem with doing this with P equal 1, say, is that we might have we don't have too many edges that are saturated by some simple double counting, but we might have many pairs of edges that are saturated. But by passing to a random subset, this reduces the pairs of edges that survive by a factor of p cubed, right? Because a pair of edges, we're keeping the vertices with probability p. So the worst case is when you have two edges that are incident, and then that's probability p cubed of surviving. So edges have probability p squared of surviving, or perhaps p squared is here, and pairs of edges have probability p cubed of surviving. And so by choosing p correctly, we can make sure that the number of pairs of edges in this random subset are smaller than the number of edges that survive. And so what survives has order Pn to the 3 over 2. Actually, some large constant. Okay, this is by choosing P to be some large constant over k squared, we get some large constant times Pn to the 3 over 2. But this is good because we have Pn vertices and Pn to the 3 over 2 edges, and therefore in what's left, we have at least one copy of C4. Right? Just by the usual extremal counting cherries argument to bound the extremal number of a C4. Okay? So we pass to a random subset, we kill all our dangerous edges that are left in this random subset, and then we observe that we expect to have enough edges left in order to find a C4. Okay. So, in fact, we don't just find one copy of C4. So a very simple supersaturation argument says that we find about Pn to the 3 over 2 copies of C4. So how do you do that? Well, it's incredibly simple. You apply the extremal result to find one copy, remove an edge from it, and repeat. Each time you find a C4, you remove one edge, but because our number of edges is more than twice the extremal number, we can do this extremal number of times before we fail. So this greedy argument gives us the extremal number copies of C4. Okay, so stupendously simple, and that's enough. Each of these was included in this induced subgraph with probability p to the 4. So by double counting, there must be at least this many copies of C4 that can be added to A. Okay, so p to the minus 4 times this number which is exactly what we wanted. And that's the proof. It's just sensationally simple. Okay. Right, so just to say, to go through it again, choose a random subset, kill all of your surviving dangerous edges and dangerous pairs of edges. By choosing P correctly, you don't kill very much by doing that. Now use this incredibly simple supersaturation, just greedily pick copies of C4, and then do double counting to get what you want. And because we killed all the dangerous edges, all of these copies of C4 are good, and so all of them, you can add any of them to your set A, family A. Okay, and that's the proof. So that completes the proof of Kleitman-Winston, and also by basically the same argument, the theorem of Ferber, McKinley, and Samwarty, which basically solves this old problem of Erdős from the 70s about the number of H3 graphs with H bipartite. Okay, so essentially the same proof works. Okay, so you need annoyingly you need one of these two technical assumptions. Either you need so if you want to show that the number of H3 graphs is 2 to the big O extremal number, you need either the extremal number is of order n to the alpha for some alpha, or you need to beat the lower bound you get from the random argument by some n to the epsilon. Okay, so whenever you can do that, then Erdős's conjecture is proved. Okay. So let me show you another application of this. So Faraday proved a long time ago this lovely result about the Turán problem in GMP for C4. It showed that the Turán problem has these 3 different phases. So we actually proved the upper bounds, but the lower bounds are not so difficult. So if P is very small, then you can keep almost everything. That's just the same argument as normal. Count the expected number of C4s and kill one edge from each. Then there's this weird, very long flat bit, in the middle, where the extreme number stays constant for an incredibly long time, for P all the way from n to the minus 2/3. I can't highlight it, unfortunately. Anyway, the second one, all the way from n to the minus 2/3 to n to the minus 1/3, the extreme number doesn't change. It stays n to the 4/3. So the best thing in this range is to take a random subgraph and then kill all the C4s. And then at n to the minus 1/3, it takes off again. And this is because a different construction is taking over. This construction is related to the one I just mentioned, answering Hiep's question, that if you take basically the intersection of GMP with a blow up of a projective plane, and that gives you this third range. Okay. So Faraday actually proved a different theorem. He wasn't thinking about this problem, but he was counting things. But you can easily deduce this from his result. He also used the method of Kleitman-Winston. So it's also a sort of containers type result. And I should perhaps mention this construction of Koyakawa, Kreuter, and Steger, which shows that in this second range there really is some log term here, and the log is really doing something sort of non-trivial. So there's some sort of log alpha to the 1/3, where when P is alpha times this. This should be n to the minus 2/3, not n to the minus 4/3. Yes, n to the minus 2/3. So the container theorem that we proved is not strong enough to prove this theorem of Faraday, but the following container theorem is strong enough. So this is the one that David and I proved. So the differences are, the main difference is this k to the 1/3 becomes a k. So our family of containers is smaller. There's another slight technical difference. This is only valid when k is smaller than n to the 1/6. Okay, if it above n to the 1/6, it's not true. but if you just apply it at n to the 1/6, then it's still sort of, it's fine. It gives you everything you want. So there's some technical reason why that's true, and this relates to a sort of interesting phenomenon when in the supersaturation, the crucial inequality changes from delta 4 to delta 2. Yeah, so I was going to talk about that, but I decided not to. Right, and the proof is specific to C4s. So we managed to extend it to complete bipartite graphs and even cycles, but it doesn't work in general. Okay, but this is sharp. This is the correct supersaturation for C4s, the correct sort of container theorem. Right, and as I said, so we also proved it for C2K and KST.
Sorry, Rob, so one question. So if it's sharp, so why don't you get the right constant in front of for the extremal? I mean, you can show the next slide, like this theta, I think you don't get the correct, like.
Right.
So how do you, why is it?
So what should the correct constant be here? Right, sorry. So it's sharp in the sense of this k, this power of k, and maybe even the log k. But I think the constant here. So there's two constants, right? There's this constant c. There's also this constant k0.
But the constant p0 should only restrict the range of p for which you should.
Right. Yes. So right. So you're asking whether we can actually get the correct constant here. I suspect that this constant, because of this constant, you can't. Yeah. So that's an interesting that so we did not try very hard to get the correct constant. So this is quite a few years ago since we did these calculations. But if I recall correctly, if I guess correctly, then this constant c leads to losing a constant here. I think I don't promise that, but and so if you try to do the calculation and you think that's false, then let me know.
Okay, thanks. Yeah.
But that's my guess. Yeah, it would be very nice to get the right constant here. That would be very interesting.
I mean, because the lower bound construction sounds kind of good. I mean, it's like interesting construction.
Yeah.
This sounds kind of correct. I don't know. I mean, from feeling, it sounds kind of good.
Right. So at least for C4. So the other thing is that we were doing this, trying to do this for C2K. That was our main motivation. And there, right, you don't even really know that this theta is a theta, right? Because we don't have the construction.
Right. It's just talking about C4.
But for C4, yeah, for C4, it doesn't seem impossible that one could get the right constant, and that would be super nice. Yeah. I think that's a nice question. Right. So what I want to point out here, and we'll see another example of this a bit later if I manage to get to it, is that there's this long flat bit where the extremal lemma stays constant for a long time, also occurs for all even cycles, for all complete bipartite graphs. It occurs for BH sets, as proved by these people. So maybe this occurs always. It'll be interesting to try and understand this. So there's this sort of mysterious long flat bit that's happening, which I'll show another example of this in a few minutes. Okay, so I'm going to skip this application of discrete geometry because I've only have say 20 minutes left, and I want to tell you about something else. So let me just tell you the statement. So this old question of Erdős about points in the Euclidean plane, almost three in a line. Looking for subsets in general position, and Balog and Sholimoshi gave a lovely random construction using the container method by applying the lemma to the three uniform hypergraph, encoding collinear triples in M cubed. So just to run through it very quickly. So I'm not even going to do any of this. Right, so people can read this if they're interested. Yeah, suppose I'm just going to skip all of that. So another thing I wanted to tell you about, but I'll perhaps tell you just very quickly, is a recent efficient container lemma proved by Balog and Samoti. So in the original container lemma, so someone asked how small delta is. So we need delta. So it doesn't depend very badly on C, but it depends pretty badly on K. So we need it to be 2 to the minus K squared. And Balog and Samoti have improved this as follows. So they might get a delta of the form that's polynomial in K. This is a very recent result. So the rest of the lemma is the same. So for each K and C, you can take delta to be K to the minus 4, C to the minus 1. H is as before, satisfies these max degree conditions. And there's a slight difference here that the fingerprint is slightly larger, but again, just by a polynomial factor in K. Okay. So I was going to talk about this a bit, but I'm afraid I won't. But just so you know, it exists. So the proof of this is quite different. So it involves sort of some high dimensional geometry and choosing the next vertex in the algorithm in a much cleverer way than we did. So they show that you can. There's always a vertex that you can choose such that its answer pushes you towards the middle in some high dimensional geometric setting. And this gives this very significant improvement over the original. So just to give one application, so with a bunch of people, we proved a few years ago that almost all KR-free graphs R-1 partite are up to log n to the 1/4. This is an old result of Colatis, Kleitman, and Rothschild, I think, for R fixed. With efficient container lemma, they managed to prove this all the way up to log n over log n, which is almost best possible, because above log n, I mean, being KR free tells you almost nothing. So almost all graphs are 2 log n, K 2 log n free. Right. So there's interesting threshold but as you move from log n over log n to log n. Interesting to understand. Okay, I'm sorry, and this is the exercises. Right, so I'm now going to skip to my final lecture for the final 20 minutes. Where are we? Here we go. I'll try and share that. So I wanted to tell you, which one are we? Lecture 4, here we go. Right. So I want to tell you a little bit about another recent development, which is the asymmetric container lemma. So just to put it up again, so this is the original container lemma, and for some applications, this version is not enough. So this is what I find sort of the most interesting about this theory. So finding problems where you feel like it should be a container problem, but the original container lemma doesn't work for some reason, and this is sort of driving us to find new versions of the container method for these settings. So plan for today, or plan for the next 15 minutes, I'm going to just try and discuss these two applications of the asymmetric container lemma. So the first it was the original motivation for it, discussing almost all induced C-free graphs. Those sparse induced C-free graphs are typically not structured when m is smaller than n to the 4/3, and they are structured if m is larger than n to the 4/3. So a split graph is a graph that can be covered by an independent set and a clique. And such graphs, whatever you do in between the independent set and the clique, you do not construct any induced C4s. Okay. And I also would like to mention briefly this result of my student Marcelo Campos. So this is about the number of sets, subsets of 1 up to n of a given size, and with a given bound on the size of the sumset. Okay. Okay. Right. So So how can we prove a container theorem for induced C4 free graphs? Well, a natural way to do it would be to apply the usual container method to a 6 uniform hypergraph whose vertex set are 2 copies of the edge set of the complete graph, which correspond to edges and non-edges. And the edge set would be all induced copies of C4, meaning you have 4 edges in one copy and 2 non-edges in the other copy. Right, so it's sort of 4, each hyperedge would have 4 vertices in the first copy and 2 vertices in the second copy. Okay, so that's a way to an induced C4 free graph will be an independent set in that hypergraph. And this works, but the tau that you get is the same as for K4 because you're essentially encoding copies of K4, right? So you're saying that you have to edge, 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 non-edge, non-edge. That's a copy of K4. And so you can prove a weaker version of this result. So M is when M is bigger than 5/3, you're structured instead of 4/3. There's this gap between into the 4/3 and to the 5/3. And it's basically because we're dealing with the upper bound with K4s instead of C4s, which is bad. Okay. For me to do is take advantage of the asymmetry between edges and non-edges, which is particularly the case in sparse graphs. So when we're looking at a graph with M edges and M is small, then edges are very valuable. Non-edges are basically free. Like almost everything is a non-edge, but there's only a few edges. And so edges and non-edges, there's no symmetry between them. Okay. So instead of constructing a family of containers for all induced C4 free graphs, we construct one only for those with M edges. When M is small, our number of containers will be much smaller. Okay, so instead of trying to obtain these containers for all independent sets, let's just find them for independent sets of size M. Okay. Right. So to do this, we need a modification of the container lemma. In each step, instead of throwing out delta proportion of the vertices, we either fix delta proportion of the vertices to be non-edges. So delta proportion of these, of the edges of our complete graph, we fix them to be non-edges, or we fix delta M of them to be edges. Right. And in either case, we only need a constant number of steps before we've basically fixed almost everything. Right. And this lemma turns out to follow from the same proof with just one twist. And the difficult part is as you come up with the right conditions on H to make it work. And the conditions are quite a bit more technical than the original container lemma, so I don't really want to state it and terrify you. The original one is complicated enough. But anyway, what this allows you to do, together with a suitable balanced supersaturation theorem, is to get a fingerprint of size about M, and so to get few containers. This is a very, very rough outline of what one does. And just to give you an idea of the supersaturation theorem that we prove, then it looks like this. So this is a sort of a simple consequence that's a bit easier to understand. So if you let F and G be disjoint graphs on n vertices, so F you should think of as the pairs that we're fixing to be edges, and G are the guys that we haven't yet decided if they're edges or non-edges, and then everything else we've decided is a non-edge. So we start out by not knowing whether if we have the complete graph, every pair could end up being an edge or a non-edge. And then as we apply the container lemma a bunch of times, we're fixing certain pairs to be edges and fixing certain other pairs to be non-edges. And then we have a bunch of pairs that we don't yet know. And that's G. Okay? And F is the things we already fixed to be edges. And under these conditions, then we show either F is basically a complete graph, or there are many copies of C4 in G whose vertex is independent in F. What does that mean? A copy of C4 in G means those things could all potentially be edges, and the vertex set being independent in F means the other two could potentially be non-edges. And so these are potential good copies of C4 in our kind of partially decided graph, or it's sometimes called a pre-graph. Just give you a picture. So this is sort of the extremal thing we're thinking about. So this is so we have a complete graph on L vertices. We have a complete graph across, or sorry, we have an arbitrary graph across and an independent set over here. So we're thinking about this L clique is F, the complete bipartite graph is G, and then everything over here is a non-edge. So this is the extremal thing, extremal construction for this the supersaturation theorem. Okay. Okay. So sorry, that was an extremely fast overview of how to prove this result, but right. So I guess I encourage you, if you're interested,
Sorry, Rob. So you want the edges between this clique and the independent set to be there? I mean, E of G.
Sorry, these things in between are the edges of G. So I should have given them a different color, perhaps.
Yeah.
So this
should be kind of complete, right? So according to the
so there would be complete. It's complete, but the edges of G are what we call mixed edges, which means you don't know yet if they're going to be an edge or a non-edge.
Mm-hmm.
So this is a family of graphs where every mixed edge is free, and the guys on the left are fixed to be edges, and the guys on the right are fixed to be non-edges. Right, and this contains none of these graphs contains an induced C4. Right, so this is like our current container for what we have so far. So we're sort of pushing it towards things that look a bit like this. And that's how we end up getting the structure of a typical guy, because basically we get lots of containers that look like this guy. Yeah. Right. But it's very important when doing this that we use this asymmetric container lemma. Okay, so just my last very few minutes. So before moving on to the last very few minutes, let me answer the question I asked at the end of yesterday, which is this strange thing that says, let G be a random graph, the GMP, but conditioned on this weird event, there's no induced copy of C4. How many edges does G have? So if anyone predicted this, I'd be very impressed. So first, perhaps you could guess that if P is small enough, then it just looks like GMP. If P is bigger, then between n to the minus 2/3 and n to the minus 1/3, then G doesn't gain any more edges. So restrict this conditioned event says that basically typically GMP will just be much sparser than it's supposed to be. So if you take GMP with P being n to the minus 1/3 and condition it to have no induced C4, it will look like GN n to the minus 2/3 that just gets lucky and doesn't have any copies of C4, which is sort of crazy, right? This conditioning of having no induced copies, the easiest way to avoid C4s is just to be a much, much, much sparser random graph. Up to about n to the minus 1/3, at which point the easiest thing is to have this little clique which kills all the induced C4s and this large independent set. So suddenly at n to the minus 1/3, you then get this very GMP conditioned to have no induced copy of C4. The easiest way for it to do it is to look like a split graph. Okay. I find this super surprising. And we again see this long flat pit in this induced question. So I sort of meta conjecture that this always happens, without really knowing exactly what that means.
You mean like for like degenerate problems, right? Like
yeah, for degenerate problems, exactly. For H by part, and you're right. Perhaps in more generality for degenerate problems. Yeah, indeed.
It'd be much more complicated if C4 is replaced by 8, right? An arbitrary graph. So then you can see much more complicated behavior.
Yeah, right. So potentially you could see, so perhaps several jumps. Yeah, that would be interesting. Yeah, absolutely. Or for an arbitrary hereditary property of graphs, then you could really see something like this, right? So arbitrary monotone property of graphs or an arbitrary hereditary property of graphs with many forbidden things, then all kinds of crazy things can happen. Yeah, it would be it's interesting to. So for monotone things, the original container lemma basically deals with all these problems. For hereditary properties with forbidden induced subgraphs, then we know very little. So yes, particularly in the degenerate case. Right. So very finally, in my last 5 minutes, I want to tell you just a little bit about sets with small sumset. So here's what a sumset is. Just it's all the sums. So interesting this question of Green about the number of sets of size k with sumset at most m. So he was motivated by study of Cayley graphs, and in a paper on the Cameron-Erdős conjecture. So Alon, Balog, Samity, and myself, we made this conjecture about it's an approximate answer to Ben's question. So basically, we said that this m over 2 choose k comes from taking an arithmetic progression of length m over 2 and choosing an arbitrary subset of size k. Right? Any subset of an arithmetic progression of size m over 2 has automatically a sumset at most m. So this is sort of the best way to do it, as long as k is not too small and m is not too large. Okay. The lower bound is just k subsets of an arithmetic progression. Okay, so with Ben, we managed to prove this when m is big OK. So for bounded doubling. So bounded doubling, so Ben had some very clever methods using Fourier analysis that allowed one to prove a sort of regularity lemma for such objects, and using this regularity lemma together with the Cauchy-Davenport theorem, one can prove this theorem with some work. But this breaks down when m is any larger. Right, uses Fourier analysis. But Marcello managed to prove this in almost full generality using asymmetric containers. So he took this m from order k all the way up to k squared over some polylog. And even more, he observed that it's false if so you really need some polylog. So the simple construction, which actually was in my paper with Ben, which shows that it's so probably I should give credit to Ben for that. That it's false if m is bigger than k squared over log n. Okay, this is using the asymmetric containers. So I won't tell you anything about that. So I was going to tell you about this container theorem, but it's perhaps a bit too complicated. Just to note that the size of the family of containers. So this is on so 2 vertex sets. One corresponds to A and one corresponds to A plus A, and the size depends on M. So this is really using this asymmetric containers really comes in to give you you're just finding a bound for the sets with small sumset. So just like we were finding a bound for the induced C-free graphs with M edges, here Marcel is only finding a set of containers for the family of sets with small sumset. Okay. So perhaps I'll just skip over this.
Sorry, Rob, but for this, you can use this asymmetric container lemma as kind of a black box and just feed in some numbers, or you have to reprove. I mean, like your student Campos has to reprove the theorem for this hypergraph sort of.
No, so he used the asymmetric container lemma that David and Wojtek and I proved in the C4 paper, the induced C4 paper. The proof is very similar to the original proof of the container lemma. It's just there's one extra trick. The statement is more complicated, but the proof turns out to be very similar. Yeah. So the clever idea, Marcel's clever idea, was to come up with was to think you could apply it here and to come up with the correct hypergraph, which is not the obvious hypergraph you would think of, or it was surprising to me. Yeah. So there's sort of the hypergraph, taking these two copies of this A and this A plus A, and taking pairs here, A and A, and then not in A plus A. It's sort of in hindsight, it feels obvious, but it was super non-obvious to us. Yeah. Anyways, there's lots of lovely applications. So I have 0 minutes left. So I'm going to tell you one final application, my last slide. So Marcelo managed to get this approximate structural theorem. So almost all sets with small sumset are close to an arithmetic progression. So with Marcelo and also Mauricio Corollaries, Natasha Morrison and Victor Souza, so we proved the following sharper result for bounded doubling. So if your set has size k and sumset at most constant times k, then there's an arithmetic. It's contained an arithmetic progression of size basically as small as it could possibly be. So lambda k over 2 plus a constant. And this constant depends on lambda and the probability that you want this to be true, so the proportion that would be true. And actually our constant depends on these two things in the correct way when epsilon goes to 0. So this constant is of the order lambda squared log 1 over epsilon when epsilon is small. And just to say, the proof is apply Campos's theorem to get the rough structure. So work a bit, and then apply it again to get the precise result. This for those people who've proved things like this is quite surprising. Usually use containers at the beginning, but then you do something else to clean up to get the precise result. Here we use containers to get the precise result, and also a third time to prove some probabilistic lemma. So this container theorem is really kind of it seems very flexible and gets used in all different kinds of ways in this proof. And I just got an email this morning saying this paper had been accepted, so that's also quite nice. Anyway, so let me finish with an exercise about maximal triangle-free graphs, and I've run out of time, so I'll stop.
Thank you very much. It's been a wonderful set of lectures, a wonderful week. So we'll have some time for questions, but I'd like to invite them to open mics and please show our acknowledgement and thanks to Rob for these lectures. Okay. So are there? So the last day you're not supposed to hand in the exercises, okay? So are there questions more or?
Sorry, so maybe one question. So that this looks very interesting that you say that you can prove the precise result using the container again. So does it have potential to be used in other contexts as well, or is it something very special about this?
So sorry, that's an excellent question, and I do not know the answer to it, but I think it's absolutely something that people should investigate. This was very surprising to me. So Marcelo had this really clever idea to do this, and I haven't seen it in any other context. There we go. So I haven't seen it used in any other context. But I absolutely don't see why it shouldn't be possible to use similar ideas in other places. So yeah, my hope and my guess is that this is actually an idea that will have lots of applications. So yeah, I very very much encourage people to try to do this.
Thanks.
Yeah.
Perhaps not a question, but a little comment. In the first lecture, somebody asked about containers for directed graphs, but I think I had already left the room. It's more of a wave to there was this master student of Yoshi that did something with digraphs and containers. His name is Bruno Pasqualuto Cavalar. He's in doing his PhD in Warwick now.
Ah, very
Just
nice. And if you have a link to the paper,
Oh
you
yeah,
can,
I think I have. It's
that'd be nice.
yeah. Okay, I can. Oh, let me find it here.
Yeah, so of course there are many many applications that I didn't have time for. I mean, I didn't have time for the applications that I chose. So, but yes, I think there's sort of lots of different directions in which people are taking this, and yeah, it's wonderful to see. And I hope that people. I hope that some of. So I should say that. So Marcelo, the first mini course I gave on containers in Sao Paulo, so 4.5 years ago, Marcelo was attended the lectures, and when he was still in high school at the time, and so within a couple of years he had proved this theorem, his container theorem. So yeah, it's I hope that that some of you will follow in his footsteps, and some of the young people will be proving things very soon with this method.